chapter. So there's a whole chapter where we do this. This is supposed to just be a quick dip your little toe in the water and pull it out really fast. We're not going to go much deeper than just the tip of our little toe. So, a scatter plot. A scatter plot is a plot of the ordered pair, x, y, where x is some random variable and y is some random variable. And these are random variables of quantitative data. This will be used to determine whether there's a relationship between the data. And so bivariate data. An ordered pair is said to be bivariate data if each of these are random variables. So let's say height and weight. So this is maybe for each person, I will ask you, what is your height and what is your weight? So here's your height here, and here's your weight. And for the next person, here's your height, and here's your weight. So a correlation. A correlation is some relationship between the variables. So if one variable changes, when one variable changes, the other variable also changes, then we say that there is a correlation. We'll say that the correlation is positive or a direct correlation if an increase in one variable causes an increase in the other variable, or a decrease in one variable causes a decrease in the other variable. A correlation will be said to be negative or an inverse correlation if an increase in one variable causes a decrease in the other variable. So a decrease in one variable causes an increase in another variable. So they're going in opposite directions. They're the inverses of each other. A linear correlation coefficient is a sample linear correlation coefficient is denoted by the letter R. It somehow measures the strength of the linear association between two variables. There'll actually be R squared that really measures this, but R is related to it. And so, if I look here, well, there's a positive correlation. As the x's increase, there seems to be a corresponding increase in my y values. And these seem to be somewhat linear in fashion. They seem to be closely bunched towards some sort of line here. And so this has a positive correlation, and the linear correlation coefficient is 0.851. So it's a pretty, and so think of that as 85%. This is in percents. So it's around 85% linear correlation. My If I look here, well, they seem to be in a negative correlation. As my x's, as my one of my variable increases, the other variable decreases. And so this has a negative correlation. So R is going to be negative. So in this case, R is negative, and negative 0.965. So about 96.5%. So it's pretty linear. It's about a 96% linear. Now, of course, what I'm saying is not quite correct. We'll say it more correct in latter chapters when we actually do this. So I'm saying 96% linear, and that's not really a true statement, but it gives you an idea. This is like 85% linear. This is like 96% linear. And explain it in a better fashion later. Next, if you look here, well, there doesn't seem to be any correlation. You know, if you go up or down one of the variables, that doesn't cause the other variable to either go up or down. So there's no correlation. The correlation coefficient is like 0. Next. If I look here, well, this seems to be some sort of correlation. It seems to be a parabola. So we seem to have a quadratic relationship here. So here it looks like a quadratic relationship. It looks like a parabola. It doesn't look like a line. So there is some correlation, but there's no linear correlation. So this is virtually 0. So the linear correlation coefficient is essentially 0, negative 0.087. And so there's no linear relationship, no linear correlation. But there is a nonlinear relationship. Requirements for linear correlation. The sample of paired data in a simple must be a simple random sample of quantitative data. A visual examination of the scatter plot must confirm that this is indeed approximately in a straight line pattern. And you must not have any outliers. The outliers must be removed if they're known to be errors. Otherwise, the effect of the other outliers, those that cannot be removed, has to be considered in calculating R. So you need to calculate your correlation coefficient both with and without outliers, because they'll greatly affect the shape of your, the slope of your line. And so the position and slope of your correlation line, your regression line. So regression. The regression equation expresses a relationship between, well, the explanatory predictor independent variable and y, the response dependent variable. So a the typical equation for the equation of a straight line is y equal mx plus b. In statistics, we will express that as y equals b sub 0 plus b sub 1x, where b sub 0 is the y-intercept and b sub 1 is the slope of your line. And so your regression line is the line of best fit. It is the least squares line. It is the straight line that best fits your data in your scatter plot. And so, if I'm talking about a population, the y-intercept of the regression line is denoted by beta sub 0. For the sample, it's denoted as b sub 0. The slope of the regression line for a population is beta sub 1. For a sample, it is b sub 1. The equation of the regression line for a population is beta 0 plus beta 1x. For a sample, it is b sub 0 plus b sub 1x. And we usually put this little caret above this little caret, this little hat above the y variable to denote the fact that this is your regression line, that this is your expected value of what y is, but it's not necessarily your actual value. It's just a calculated value of y. And so, if I had some data here, then this would denote my least squared line, my regression line. Would look something like this, that would fit this data. And that's all we really wanted to say about correlation and regression. We will be looking at it much more. We have a whole chapter that we will be discussing it much later when we have much more mathematics under our belt before we can really look at it